Okay, let's go ahead and get started. So just missing, oh no, Robert didn't jump either. Okay. All right, so most of you have the test done. Oh, there's Cassie, good. Hi, Cassie, we're just getting started. Okay, so do you guys have questions that you want to review this morning before we do new stuff? So this, the next test is kind of a short one in terms of number of sections because it's only got the last three sections from chapter 3 on it. And so, and then we'll have the midterm exam window, but it's kind of goofed up. So I'm gonna, it's not right, I don't think, on the schedule.
I have a question.
Shoot.
Can I share my screen, possibly?
You should be able to.
Okay, let me open it up real quick.
Okay.
Okay. All right, I'm sharing it right now.
Okay, thank you.
Can you see it?
I can.
Okay. Yeah, so can we go over this one?
Is this from homework or is this from the test?
Homework.
Okay. Yes, we can. I just wanted to make sure because some people haven't done the test yet, and
I can go through every one of my test answers. No, I'm just kidding.
Okay, so what they said was evaluate the integral, but don't solve for the coefficient in the partial fraction decomposition. So in other words, we're not going to figure out what A, B, C, D, however many letters we have. We're not going to figure out what those are first. We're just going to write it up as a partial fraction, and then we're going to evaluate the integral. So this is kind of an interesting way.
I know how to do it, except I know how to do like most of it. I'm just confused about the C and the D part. That's the only thing I'm confused about.
Okay, well,
I know how to do the A, B and stuff, but
right. But let's go through and work through that.
Okay.
So and then notice they had to use the letter K for the constant.
Right. Yep.
Because they were working with end this, end office hours. Come in here. They had already used C in the partial fractions part. Okay, so I am going to, let's see, 1 over. Okay, so this one is kind of weird in that we've got this funky quadratic factor, and I'm guessing that that's where the C and the D gave you troubles there.
Yeah, well, see, I thought it would just be CX plus D, but.
Well, it is. It is for the numerator, but then remember you have to evaluate the integral. So let's write it down and see.
Yeah.
Okay.
Yep.
I'm going to take away your sharing.
Okay, and I did do the complete. I did have to complete the square to get it in terms of for the tangent inverse.
Okay, so let's go ahead and write down this integral and write down the setup. Okay. So we got 1 over 2
and I'll just redo it.
Plus 1 squared times x squared minus 2x plus 2. So this is probably the most messy that they're going to come up with on here. And then I need my dx. Let's fix that fraction bar so it goes all the way across. So I see first a repeated linear factor. And then I see a quadratic factor. And so I'm going to set this up as one fraction for each power of the repeated factor up to however many there are. So that should be an A, with constants in the numerator, plus b over 2x plus 1 squared. So I think you said you were okay with that part of it. And then a linear expression over the x squared minus 2x plus 2 dx. So that would be the setup for the partial fractions. And this is a really nice problem because it sort of took away the ability to, you had to be able to set it up, and it took away the ability to just have, say, Mathematica or a calculator or something come up with the answer to the integral, right? Because you needed to write it in terms of these constants a, b, c, and d. Does that make sense?
Yeah, that's exactly how I set it mine up too. I was just rewriting the problem down, so I would have said that earlier, but I was looking at my other screen.
All right, so now let's look at this just in pieces. So the first one is integral of a over 2x plus 1. And a is a constant, so I can factor it out.
Yep.
And then I could let u equal 2x plus 1, so du equals 2 dx. And that means dx is du over 2. So this is a times integral 1 over u du over 2. I'm going to pull my over 2 out front. So that one looks like a over 2 times the ln of u plus a constant, or a over 2 ln of 2x plus 1. And then we'll have plus the constant at the end. So that's one of your choices. So in your choices in the homework, you're going to look for the ones that have that for the first term, but I'm guessing there's more than one of those, so we don't
all of them but one, I'm pretty sure.
All but one? Okay.
But I could be wrong, but I know that a lot of them have it. You can't just do that one and pick them, you know?
Right. Now, the next one, b over 2x plus 1 squared. So again, we're going to factor the b out and then think integral 2x plus 1 to the minus 2 dx. Notice here that we would use the same exact substitution as the last problem.
Yep.
So I'm not going to resubstitute because it's all right above there. But I would get then b over 2 times integral u to the minus 2 du. So let's see, that's b over 2 times u to the minus 1 over minus 1. Okay, or minus b over 2 times 2x plus 1. So now we need that term as our second term. So we've got this as one term, and then there's our second term. And then the cx plus d part, you're right, you did need to do a little bit of completing the square to get that into the form you want. We're also going to look at another method for that today.
Like that we would have to do for this problem, or that you're going to teach us? Like
no, that you could use instead of completing the square.
Oh, okay.
But for now, It's really all we've got. And there's also this other little glitch that we're going to have to work on this part with separating fractions, which is just a neat little algebraic trick. So that denominator, and I'm just going to save myself a little bit of space. And I'm going to pull out an x squared minus 2x. To complete the square, I'd want half of 2 is 1 and 1 squared is 1. So I would want a plus 1 there.
Right.
And that means I'm just really splitting that 2 up into 2 pieces. Plus 1, because I already had 2 dx. So this is integral cx plus d over x minus 1 squared plus 1 dx. And so, so it's kind of looking like an inverse tangent.
Yeah, it is.
Substitution. So did you let u equal x minus 1 first?
Yeah.
So du equals dx.
And then 1 equals a, but we haven't gotten there yet, I guess.
And we don't even have to, so 1 equals a? I don't have an a here. We're not going to solve for c or d, remember.
Right.
Okay. Right. I'm not sure. Oh, 1 equals a. Gotcha. That a. I was thinking capital A from up above. Okay. Yes, you are right.
Okay.
So a equals 1. So just being a little careful because my numerator isn't just a number. This looks like integral of c times u plus 1 plus d.
So, wait, you just plug, okay. Yeah, I guess.
Yeah, so if u
I get it.
You see that x is u plus 1.
Yep.
So then, let's see, I've got integral of c times u plus c plus d all over u squared plus 1.
Any way you could scroll up, possibly?
Yeah, so here's the thing. That's one trick about the Zoom whiteboard. It doesn't let me scroll up.
Okay, that's fine. I can.
So take a note of that one.
What note of what one?
Oh, the page, because we're gonna in fact.
Don't change it yet.
I'm gonna do a quick screenshot just in case things go wonky on me, so I have that all on my computer. And I'm gonna go to the next page. Let's see.
That was an x squared plus 1 at the bottom, right?
Yeah, hang on.
All right.
This is why I made that screenshot so I could see this. So it was a u squared plus 1 in the bottom. So at this point I had this.
Wait, the second to last step?
I'm gonna put that last line I had up there.
What about the second to last step? Was that a huge too?
That was a u squared plus 1 in the denominator also.
Okay, cool.
The second to last step was just this step before I distributed the c.
Expanded it. Okay.
Yeah.
All right.
Okay, so now I'm going to split this up as c times u over u squared plus 1 du plus c plus d over u squared plus 1 du. So my first integral, I'm going to do a substitution, and I already used u, so let's let v equal u squared plus 1. And dv is 2u du. du is dv over 2u. So I've got c integral u.
Wait. Okay, never mind, sorry.
So I'm going to get another 1/2 there. Notice how you got that 2 from the du in the denominator. So that term is going to give me a c over 2 times the ln of v. Just from that term. And then
what does that say at the very bottom there?
c over 2
Okay.
times the ln of v plus a constant.
ln of v?
ln of v. Remember, we have a new substitution.
Right, all right.
All right. Then in the other term, the c plus d is a constant. This actually ends up being the nicest one of all because a is 1, so that's plus c plus d times tan inverse of u. And we got to get everything back in terms of x's plus put our whole problem together. So if I go back and look at my screenshot of my notes that I had from earlier, here's my answer. It was a over 2 times ln of 2x plus 1 minus b over 2 times 2x plus 1.
Could you multiply that out?
I could, yep. That denominator, you mean?
Yep.
Yep, absolutely.
Cool.
And then plus c over 2 times the ln of v, but v was u squared plus 1, and u was x minus 1, right? So that would be u minus 1, or not u, just undo. X minus 1 squared plus 1. And if you multiply that out, that's going to be that original x squared minus 2x plus 2.
Okay.
Okay, so c over 2 ln of v. Okay, that's good. And
Are those absolute value bars?
Finally, actually, I did not put absolute value bars there because that's a sum of squares. So I know that's always positive, and
okay.
So I don't really need them. They wouldn't be wrong to be there, but they'd be redundant. So if they have them in their answer, that's okay. We can still choose that. But they're not necessary.
Okay, thank you.
Because a sum of squares with real numbers is always going to be positive, right?
Yeah.
Okay, and then finally we have this c plus d.
Wait, you said a sum of squares is what? Is always going to be positive?
It's always going to be positive as long as our numbers are real numbers.
Oh yeah, okay, yep.
So c plus d times tangent inverse of u, which was x minus 1. And finally plus a constant. So now can you go ahead, let's let this sit for 60 seconds or so.
Okay.
And let everybody make sure they've got this much. And then I'm going to stop my share and let you go ahead. And in fact, I'll do this just in case something screwy happens. I'll stop my share and you can go ahead and share your problem again.
Okay.
Share your page again. So.
I'm going to share it right now.
Yeah, let me actually cancel. I got to stop it from here. All right, there we go. Go ahead, Gabe.
Okay. Thinking this to give me an answer.
All right, so yeah. Yeah, and notice they did leave those absolute value bars there.
Yeah,
But they really don't need to be there because that expression is always positive. The first set of absolute value bars they needed. Oh, I wrote the problem down wrong though, notice. I think I wrote 2x plus 1, but nothing else changes.
Oh.
Nothing else, that didn't affect anything else we did. Since we didn't solve for A, B, C, and D, that's not going to adjust our
I don't
problem.
think you wrote it down wrong. Did you?
I think I wrote 2x plus 1 when I did it.
Oh.
Yeah, I did, instead of 2x minus 1. But all of those 2x plus 1s would just turn into 2x minus 1s. Everything else is the same. And yeah, who asked if we could multiply that out? Notice they did multiply that out. B over 4x minus 2.
So all of the x minus or x plus, sorry, 2x plus 1s
Were 2x minus 1s, right? That's the only thing that changed.
Okay.
We didn't do anything that ever mattered really, whether that was a plus 1 or a minus 1.
So is this my answer then?
So it looks like your answer is the second one. Yeah, that's what I would say. Because the first one
Doesn't have the a over 2. It doesn't even have
and it doesn't, and it has the second term wrong too.
And this one's, yeah, so it's either the second, third, or fifth. Going off the second term.
Right. But it's the second one.
Wait, what's the difference?
Notice the third one is even missing the log of the x squared minus 2x plus 2, so it's out.
What about the last one? What's that?
The last one, they put a c minus d in there instead of a c plus d.
Right. Is it still c plus d even though it was 2x minus 1?
That had nothing to do with it. Remember, those numbers were from our numerator and that other term. So they were nothing to do with that being a 2x plus 1 or a 2x minus 1.
Okay. So it's in this one then?
What'd you say?
This one then?
Should be.
All right, cool. Thank you. I'm going to stop sharing. Yeah. Yep.
Okay.
I'm going to stop.
All right. Any others? Welcome, Robert. I just saw you pop in.
Does anyone want to see this right here?
Okay. Other questions?
You can do this one.
No, okay, we're not going to play this game though.
No, I was just kidding. I was just kidding.
Okay.
No, I promise I was kidding.
Okay. Now, okay, so notice answers here. So a couple of things to keep in mind. You definitely want to be able to do these problems, right?
Oh, yeah.
So you need to do the problem and work through it. But when you do have a problem like this where it's asking you to evaluate a definite integral, keep in mind that you could go and check this using a calculator or using Mathematica to make sure that you have your answer correct.
After we do it on paper.
Yeah.
Okay.
Or, if you want to do it before and then see if you match up when you get done, you could do that. But yes, you should do it on paper and then you can double check. That way you can avoid having to do 75 different problems.
Yeah.
And how many tabs do you have open in your browser, Gabe?
Not enough.
Oh, it's driving me crazy. Actually giving me like.
This is my home computer because my other one broke. Like it just broke like this weekend or whatever. So I'm using my home computer and on my other computer, and I've only had this open for since Saturday, like after I was done at work, so like 4 o'clock or like 5 o'clock since Saturday. And if I had my other one my actual computer, there'd be like 30 more tabs open.
Oh, it just drives me crazy. Okay. Anyway, all right. Other questions?
Stop sharing.
Yeah, I think we're good. Thank you.
Yep. Thank you for helping me with that.
No problem. Are there others? Okay, so that kind of went through. I have a couple of recordings that I did. I don't remember what day I did them, but I will pop them up. They'll just give you a couple more examples of partial fractions. So if you want to take a look at those, you can. I'm not sure how I'm gonna. They're just on my iPad right now, so I have to just figure out how to send them. I might just send them an email. I'm not sure. But they're essentially written out on my iPad with voice recording behind them. So they're not done in Zoom, which means sending them to YouTube might be a little bit stranger. But are there other questions? Who still needs to work on the test? Actually, I want to put this up. Uh-oh, Erin. So that was what you didn't get quite done, huh? Well, thankfully, it's only 2 points, so it's not a huge deal if you get it done a day later, so. Right. Okay, so this whole idea of partial fractions can get very messy. I do want to show you a couple things in, now I can't find things because my computer decided that it doesn't want to know where things are. So. Oh, weird. Okay, so I do want to show you can you guys give me a reminder? Who's got the Inspire CAS and who's using Mathematica, or maybe who's using both? So just a quick note in the chat. Calculator, Mathematica, or both?
What about neither?
Okay, well, you can say that too, but it's probably not a good choice because you can check so many answers there.
Are we allowed to check answers?
There are going to be some cases where you're going to want to be able to do especially some of the algebraic stuff so that you can shorten problems a little bit.
Are we going to be able to on a test?
Yes, you are.
Okay.
I mean, I'm going to ask you for all the work that's required if I want you to do a problem by hand anyway.
Right. But to check it, like we can use like calculator.
Right, or there might be a problem where I don't want you to spend a ton of time doing a bunch of grungy algebra to find, say, a partial fraction decomposition, and I want you to use something else to figure that out. Okay, so Cassie said both, Nick said Mathematica, Caitlin's using Mathematica, Merrick's using just Mathematica. Okay, Wolfram Alpha, which is really just a portion of Mathematica.
Will you show us how to use
Aaron C, also calculator. Aaron E, Mathematica. So let me see, I charged my calculator. Hopefully that really charged. Oh, it did, good. Okay, I'm gonna start with Mathematica. So we've done a few things here before, so this is another little piece of this. So we'll just start with this with some plain text. And I know you can't see my screen right now, so that's okay. Switch and share screen. Oh my gosh. I went ahead and did what? Okay, so the new OS has a little bit too much security in it, which means I may or may not be able to share this. Oh, I'm so angry. Okay. Dilemma, dilemma, dilemma. Let me try something else. I'm going to try to share screen from, I'm just going to say my desktop. Okay, so can you guys see anything on my screen right now? Were you guys able to see my screen at all?
I could see your background, but that was it.
So you could never see like Mathematica or anything?
I didn't know.
Okay, we're gonna try it again. It's, for some reason, it's, okay, it says it's sharing. How about now?
I can see it now. Yeah, I can see
All
it
right,
now.
cool, okay. I don't know how I managed to trick it. It wanted me to quit Zoom before it would let me share screen. I had to go change system preferences because I updated my OS over the weekend. So, okay, this is cool. So in Mathematica, partial fraction decomposition, the command is going to be apart. So you could also go in and just like type partial fraction decomposition and get info on it. But if you remember apart, then that will do the trick. And I'm going to use that fraction that we just had in the last problem that Gabe was doing. It was, if I remember right, which I wrote it down, so I should, it was 1 over, and then the denominator had a 2x minus 1 that was squared times an x squared minus 2x plus 2. And then close the denominator. And I think that should work, but we'll see if I'm missing something. And it appears I am not. Now, notice the one thing that this didn't do. So this as an output gave me the partial fraction decomposition. Notice that there is no 2x minus 1 term in our answer in the denominator. So that coefficient ended up being 0, and that could happen. And so if we wanted to do this problem and finish the integration, we would be integrating each of those 3 fractions separately. So if I give you a problem and I say, tell me what the partial fraction decomposition looks like. So your first step would be like in that last problem where we wrote the a over 2x minus 1 plus b over plus cx plus d over, and so on. And then I might say, you don't have to do that by hand. Just go ahead and you can use your calculator or use Wolfram Alpha or use Mathematica to go ahead and give you that that partial fraction decomposition. Now, if we wanted to integrate that, notice they actually gave us that as a choice, the integral of that function. A quick note on Mathematica when it writes these, log with a capital log, because it always does capitalize functions. Log means natural log in Mathematica and in Wolfram Alpha. So when they type log, they're talking about the natural logarithm, not the common logarithm. So that's a little bit different than what we're used to, and we need to sort of be aware of that.
Did you just straight up type a part, like just type that in and then put the
apart?
bracket?
Yep, you're going to take it apart, and then you put the square bracket for any function. So after any function, you need the square bracket and then your expression. So if I'm going to do it, let's do a simpler one. Let's say we wanted to partial fraction.
Wait, how do we get to this, by the way?
I'm sorry?
How do we get to this again?
This is in Mathematica.
I just type Mathematica into Google?
No, I gave you a link. I gave you a link back on the announcements page quite a bit ago, so you might have to go back and show old announcements. And the link to the Mathematica download is there. You need to get it from the Delta license server.
Because you have to pay for it if we don't?
You would have to pay for it if you didn't.
Okay.
Yeah, and we have a site license for it, so it would be silly for you to pay for it. So let's see if I want to do something, and I'm not even going to try to make this one that's necessarily difficult or non-difficult. I'll just do something with linear factors. 2x over x minus 1 times x plus 1. So there's my entire denominator, and then make sure I close it off. And there's that one. It's 1 over x minus 1 plus 1 over x plus 1. And then if I needed to integrate that, I could say x integral, and it would integrate it for me.
Which link do you click when you go to it, by the way?
Okay, so we can talk about this a little bit more later, but it's going to depend on your operating system, right? So
Okay.
You're not going to go get the Mac one if you need a Windows version.
Oh, yeah. Okay.
Okay, so apart is the Mathematica code for partial fractions decomposition. And so that's I think fairly straightforward. Remember, if you do want to integrate something and you want to have limits on that integral, you can, we should actually be able to, let's see if we can copy this integral. And try to paste that in there. I don't know if, I don't think I can do an adjust of that, but I could just go in here and say, if I use integrate instead, then I can do something like, so 1 over x minus 1 plus 1 over x plus 1. And if I needed this to be a definite integral, I just add the phrase x goes from, let's go 2 to 5 maybe. And that gets set in braces. So a little note about. So 27 halves plus log 4, remember that's really natural log of 4. So those aren't too awfully bad. I am really sniffy this morning. Okay. And then you can hit numerical value. It will approximate it for you if you're looking for an approximation. So that's just a nice way to check those. On the calculators, either on the 89s or on the Inspire, let me think. So if you go into the menu and into algebra, the thing you want is actually expand. So if you do expand on the calculator and then enter your fraction, it will give you the partial fraction decomposition. So expand is the calculator equivalent of a part. I'll be right back. I gotta find some Kleenex. Okay, so does that make sense for either using Mathematica or using your calculator? Does anybody need to see that on the calculator? It's pretty straightforward. There's no extra, there are no extra variables needed or anything. You don't even need a comma X. So for example, if I just do expand and then do whatever fraction I want, like that 2x over, I'm just going to type in x squared, oops, x squared minus 1. It should just give you the result, and then you usually get a message that says something like domain of the result might be larger than the domain of the input. Okay, so I will make the assumption that you're going to be able to use one or the other on these. For example, there's a good chance you'll get a question that says, write the setup for the partial fraction decomposition, which would be like the a over something plus b over something plus cx plus d over something. But then don't work through it by hand. Use some sort of technology to come up with the result of that and then integrate it. I'm going to leave that for you guys for just a second. I think that it just didn't like me sharing my entire screen. So as soon as I was sharing just a single app, it was okay with that. Okay. Okay, so this is actually taking us to the OpenStax textbook. If you have the paper copy of the book, you can do that there. But if you don't have the paper copy of the book, one thing that you'll want to be able to do is find the online table of integrals. So there's a huge table here. And it starts out with some basic integrals, so these should look familiar to you. And then it jumps up to some trig integrals. Notice this basic integral list ends with the inverse trig functions. Then we jump up to some trig integrals and all sorts of funky things in there. And you'll notice that when they get to number 28, these are those reduction formulas that we talked about. And then 34, 35, 36, these are some sort of product to sum formulas that get you out of having a product of two different sine functions or a product of a sine and a cosine. And then they jump to some exponential and log integrals. So a little group there. The hyperbolic functions are in here. Inverse trig integrals. So this is actually integrating the inverse trig functions. Integrals involving sums of squares, differences of squares, u squared minus a squared. Differences of squares going the other way around, a squared minus u squared. Integrals involving 2au minus u squared, so just some oddball things. Linear expressions, so a whole group. We are up to number 113, and I think that's it. So this table has 113. I've seen tables in calculus books with 150 or 200. I've seen tables that have a few less. There are huge volumes of, and I'm going to go ahead and stop that share. There are huge volumes of tables of integrals. They're like huge books that are just table upon table where they've gone down to specific levels. So this is just sort of a short table to give you a flavor for how this works. If you're given a problem that requires, maybe you could do it with a different method, but you can also often just go ahead and look up the problem in the table. You do have to make sure that it fits directly. So let's take a peek now back at Newton. So we'll do my homework instead of somebody else's. And I'll share again once I get in there. And so I'm going to the assignment that says integration tables and computer algebra systems. Okay. So on this, they said use a computer algebra system to solve. So in that case, they actually want you to do this with a calculator or a computer, so Mathematica or your calculator. But let's see if we can do this with the tables. So if we were working through this on the table, how would we do it there? Just because I want to sort of emphasize what we've got as options. So I am going to do this. I'm actually going to go back to stop share and see if I can share my desktop. Yes, I can. Okay, good. Get rid of that because what I want to be able to do is pull out that table of integrals. All right, so now what you guys should have is that table of integrals plus the question that they gave us, right? Hope you can see both.
Yeah, I can see it.
All right, cool. Okay, so nicely it doesn't show the Zoom chat on top of that too. Okay, so they want us to solve this using a computer algebra system, but we're gonna sort of go the table route so you guys can see how this works. Essentially what you want to do is go through until you find an integral in one of the sections that fits. Now, this might mean that you have to do a little bit of tweaking or a little bit of substituting to make sure that everything goes according to plan. So as I come through here, I notice right off the bat that I see one that almost looks like it's right. Number 16. Integral of du over a squared plus u squared is 1 over a tangent inverse u over a plus c. So that looks correct to me, but I have to be careful and make sure that everything matches up in terms of my du's and my dx's, or there might be an extra constant floating around in here. So integral 1 over 4 plus 9x squared. So what do you guys think? Do you guys have a guess as to one of those four for the answer? Assuming we have the right formula, it would have to be choice 1 or choice 3, correct? And the question just becomes, should this have a 1/3 out in front or a 1/6 out in front? I'm thinking. Cassie's guessing 1/3. Anybody else want to guess? Another guess might be 1/2, because there's that 4 there, so the a value is 2.
I got a question. Can you kind of explain? I'm kind of lost what we're doing right now.
Okay, so we're going to try to evaluate this integral, and we're going to try to use the table of integrals to do that.
And you have the table of integrals pulled up right now.
And I have the table of integrals pulled up right now. Okay. And I stopped at integral number 16. At least it's numbered 16 in this table. I stopped there because my denominator has an a squared plus u squared in it, and my numerator just has a du, which matches up with my dx.
Okay. But
they don't actually match exactly, because notice that if I'm using this formula, I must be thinking that the a value is 2. And
just factor 9 out.
And that 9x squared is going to be u squared.
Just factor 9 out.
Okay, I could do that.
Then if you factor the 9 out, you'll have your formula right there. The a will just be harder to find, but you'll still have it.
You're right. So I have two choices. I can do your funky factoring, or I can do a little substitution.
I like the factoring.
Okay. Really? You like to factor a 9 out and have fractions?
Yep.
That's interesting.
Mm-hmm. I mean, I can change it to decimals.
Well, be careful with that, because if you have something like a 2/3 and you put in 0.67, you're going to get marked wrong. So be very careful with changing those fractions into decimals, especially when they're not exact. But you are correct, Gabe. You could factor a 9 out.
And then you'll get 2/3, I'm pretty sure, for your a.
Okay. So
can't really see that. Oh, there it is.
All right. So integral 1 over 4 plus 9x squared. And we're comparing that to integral du over a squared plus u squared.
And 1 over 2/3. Yeah, so okay. 1 over 2/3.
All right, so you know what? Let's go ahead and I'm gonna stop that share.
Yeah, so shouldn't it just be 3/2 tangent -1 of 3/2 plus c?
Okay, so is that one of your choices on there?
I can't see them anymore.
Okay, and that's
you
not
still
one
have
of
to
your,
multiply-
that is not one of your choices.
Right, but you still have to multiply by 9, so let me see real quick. So is it 27/2? Someone do 27/2?
Nope, not 27/2, also not in there. So I'm gonna go with your choice, Gabe. You said you want to factor out a 9.
Right, so you'll get 9 times 4 over 9 plus x squared.
Okay, I buy that. So then you have 1/9 times the integral 1
Oh
over
yeah, I pulled it out wrong. Right, it should be
2/3 squared plus.
3/18. I'm pretty sure.
Okay, so 3/18 simplifies to 1/6. So now your a value is 2/3 and your u squared is equal to x squared.
Yeah, so it
So
should
u
definitely
equals
be
x and du
1/6.
equals dx.
Probably be 1/6, yeah. Yep.
And that formula said integral du over a squared plus u squared, since we can't see that screen anymore, is 1 over a tangent inverse u over a plus c. So 1/9 times 1 over a, 1 over 2/3, tangent inverse u over a, x over 2/3 plus c. And if we simplify everything, we get 1/6 tangent inverse 3x over 2. So that's how you would do that if you factored out the 9. So that's sort of method 1. Method 2 would be to make a little substitution. So same problem. Oops, not du. So let's undo that dx. Let u squared equal 9x squared. So we're just going to match that up in our formula, meaning that u is 3x and du is 3 dx. Or dx is du over 3. So I get 1/3 integral 1 over 4 plus u squared. And now, since my u is there exactly as it is in the formula, remember it was integral du over a squared plus u squared. That was my formula. And my a value is 2 now. I can say 1/3 times 1/2, that's my 1 over a, tangent inverse u over a, u over 2 plus c. And then plug back in my u value, which was 3x. So those are about the same amount of work either way, and it's sort of a matter of preference. Do you want to factor things out so that you have that plain old x squared sitting there, or do you want to do a substitution so you have a plain old u squared sitting there? And it's really not going to matter as long as you don't make errors along the way.
Cool.
So it was actually the 1/6 that we wanted in that choice. All right, so let's see. And I'm just going to do instructor cheat and submit. We can continue. All right, so here's a nice one. I'm going to switch my screen share back to me. Oops, I might need to fix this again so that you guys can see that table of integrals. All right, so this one is a little bit different. They didn't ask us to integrate this. They just said which one of these formulas works. And I guess actually we should be able to figure this out without seeing our big table, because we don't have to search through the whole table. This is like they gave us a little portion of the table. They gave us 4 formulas from the table, and they want to know which one of these formulas is going to give us the result on this. So what do you guys think? Well, I'm not really fond of having all these e to the x's in here when my formulas don't have an e to the x in them at all. So I'm thinking that I want to try to figure out, you know, what would my u be equal to? Do I want u to be equal to 2e to the 2x? Or do I want u squared to be equal to 2e to the 2x? So we might have to play around with this a little bit. What kind of little substitution do you guys think? Somebody give me a u that they want to try.
2x.
Just 2x.
Yep.
I'm going to insist that you use the e in your u.
Really? All right.
Or this is gonna take us all day.
Okay. Yeah, that would make sense because we have that u in the top.
And
so
notice that none of these formulas has an e to the 2x in it. So that has to be in our replacement somewhere.
Yeah, and that would work too because the derivative of e to whatever is just itself over whatever's in the exponent. So in that when there's 2e to the x's, so.
Okay, so what do you want me to let u equal?
E to the x.
E to the x. Okay, I'm gonna screenshot that question just
because then you just multiply by 4 and 2, maybe. You could just do u squared and then, or wait.
Sort of an interesting problem. So let's see. We've got integral 8e to the 4x over 2e to the 2x plus 4 all squared. All right, I stopped that share. I've got that problem. So 8e to the 4x over 2e to the 2x plus 4 all squared. Okay, so what was the last thing you said, Gabe? You were going to let u equal what?
I don't know.
No, remind me what you said. I don't think it was bad.
I was gonna say e to the x, but then because I feel like you could just like square it, but then I was thinking because then you could have like u squared or u to the fourth, but you can't have both. That's my like.
Oh, okay.
I'm
I see.
thinking. So you'd have to pick.
I see where your dilemma is.
So
Okay.
you could have yeah, you could have e to the 4x somehow and then pull something out, or you could like do e to the 4x
You know what?
the 4 times e to the x.
Okay, this is all very good because here's what I want to tell you. You're not always going to know exactly what to let u equal to start, just like you didn't with regular substitution problems, right? So I'm going to go with what you said at first, and it might work, but we might want to adjust it to maybe e to the 2x. All right, let's start here. And I'm starting here because then I know du equals e to the x dx. So a quick note about this. If u equals e to the u, or u equals e to the x, u squared is e to the x squared. And remember, we multiply exponents, so that is e to the 2x. And that means that u to the fourth is e to the 4x. Just a quick little note about exponential functions and how you square them or raise them to the fourth power.
Problem with that is we only have two e like things, so we need to remember that one of them we have to take the derivative of our substitution, so we can only use two of them, if that makes sense.
Okay, but constant multiples shouldn't really matter, should they? How about this? So that's one option right there. Another option, I'm even going to write that as option 1. And then another option might be that u equals e to the 2x. So du is 2e to the 2x dx. I kind of like this because it means u squared is e to the 4x. So it's a little bit less problematic. The other thing that I notice is that the 8, the 2, and the 4 are all constants. And if I do a little bit of factoring, yeah, I actually have one too many. No, I'm okay.
Is that supposed to say option 2?
It is. I forgot to write the 2 down. Thank you, Gabe.
Yep, thank you.
Oops, my square got lost. Square. So that whole thing is squared. Which means that my denominator is really 4 times e to the 2x plus 2 squared. Which I kind of like because now I can go in here and I can cancel and get a 1, a 2. Dx. All right, so now I'm going to try option 2 and see if it works. U is e to the 2x, so my denominator is u plus 2 quantity squared. Du was 2e to the 2x dx, so dx is du over 2e to the 2x. and that's du over 2u. And finally, e to the 4x, so there was a 2 there. E to the 4x is u squared. And I can cancel the 2's and one of the u's. So now I have u over u plus 2 squared du. And if I go back to my choices, that was actually the second choice in my list that they gave me. Integral of u over u plus a squared. So it was in there. So kind of an interesting way to do this. And sometimes you're going to end up with an expression where you might be able to actually do a problem two different ways. Now on these guys, they shouldn't give you two choices that work, but there might be more than one option. So could we have done that with this problem with option one? Maybe. It might be possible that option one would have worked. We would have used a slightly different formula, but we should still end up with the same final answer. So we have to be a little careful there. So all right, so you guys can see this problem now. This time they actually told you the formula you're going to use. So you don't have to go through and dig the formula out. You just have to figure out what everything is. So see if you can try this problem to evaluate this integral. The integral of tangent cubed a times u du is 1 over a times an ln plus 1 over 2a times a secant squared plus a constant. And we're evaluating this messy integral. It's got a whole bunch of stuff in it. A tangent squared, a sine, a cosine. Well, first things first, what is sine over cosine? What is that? Sine over cosine is just another tangent, right? Yeah, so they gave us this really ugly looking integral, but they could have much easier set up this integral as 2x times tangent cubed 2x squared. So I think on this one, you do need to do a little substitution. The a value is 2, and the u value is x squared. So see if you can get this to work and then write out what you have for your answer. We'll take answers when we're done. So give this one a try. Take a few minutes. Start by letting u equal x squared.
You said let u equal x squared or 2x squared?
Just x squared, because look at their formula, Gabe. See how they have an a in there? So the a value is the 2. So you're going to let u equal just the x squared.
Okay, thank you.
Okay, so you should have two terms in your answer. I got one half ln the cosine of 2x squared plus 1/4 oops. Okay, thanks, Merrick. And I wanted to do this because notice how I had to enter that secant squared. I don't think that it would let me do the square after the secant, but maybe it would.
It would.
It would? Okay, so unlike the calculator, it will let me do that? Thank you.
It will, yep.
Okay, so that wasn't too bad. Notice that once we did the simplifying and then the substitution, everything matched exactly, so we were able to go ahead and use that.
Want to log into my account? You can log into my account and we can go through this if you want.
Yeah. Okay, let's try one more. And then I think I'm going to let you guys go and try these. So which of these formulas can be used? What substitution? So it looks like they've got an e to the u sine u kind of thing going on, which I could see because we could let u equal 1/x and see if that one worked. And then we've got, and in fact, let's think about that. If u equals 1/x, what is du? What's the derivative of 1/x? Isn't it minus 1/x squared? There's no way the second formula can work because it totally ignores the e to the power. So the second formula is out. The third formula maybe is a possibility. And the fourth formula, maybe. But I'm thinking, I'm not sure. All right, so let's try to make the substitution u equals x to the minus 1 and see what we get. Minus e to the 1 over x times sine x to the minus 1.
Is that 1 over x, e to the 1 over x?
It is, yep, that is e to the 1 over x. Let's see if I can.
Okay, thank you.
There you go. I made it bigger so you can see it better.
Thank you.
You're welcome.
That looks a lot better.
Okay, good.
You can just let u equal 1 over x. That's what we're doing, right?
Right, which is the same as x to the minus 1.
Right, yep. Okay, I just want to make sure.
Yep. Okay, I got choice number 3 on this one.
Yeah, me too.
There, you ended up with an extra x in the denominator, but that was
No.
a 1, but that was a 1 over x, which is u. So if we submit it, they should show us what they did.
It doesn't matter what's on the right side of that equal sign,
No,
does
it really doesn't. It really
Okay, I was
doesn't
gonna
matter.
say, I didn't think it would.
I mean, it matters that they're giving you a proper formula, but you're only comparing with the left-hand side.
Is that an important formula we should probably know?
No, it's an important formula that if it shows up and you need to look it up, you'll look it up and you'll find it.
Right, but like if we wrote that down, that would be fine to write down.
Well, I mean, it would be fine to write down, but the chances of you remembering where you wrote it down are probably slim to none.
Well, I have a formula sheet, so let's write on there.
I think that you're muddying your formula sheet more than you need to.
Oh.
Because here's the thing. All of these formulas, remember, are in that formula, in that table of integrals. And so this one, where did it go? It's somewhere, not that one. All of those formulas, I mean, you could say that about any of them. You know what I mean? Every time we came upon one, you could say, okay, I'm going to add that to my formula sheet. Then you're going to have so many things on your formula sheet, you're going to just muddy the waters there. I really don't recommend adding that to your formula sheet. It just happens to be the random formula that worked on this problem. And if you did that for every problem that you did in here, your formula sheet is going to end up being cluttered. All right, which one do you think here? We're going to do one more. Is it the u over a squared plus u squared? Is it the 1 over a squared plus u squared, or the u squared over a squared plus u squared? And notice with their formulas, they are leaving out the plus c on these guys. Well, for any of these, I think I'm going to have to do a substitution and let u squared equal 2x squared. So actually this time, I think I'm going to go ahead and stop my share. We can come back to that one. And I'm going to whiteboard this one, and then we can figure out which one of those formulas works. We'll just go back to it. So let's look at the problem. The problem started with 4x over 16 plus 4x to the fourth. So I do notice a common factor of 4. And since I'd rather work with smaller numbers, I'm going to go ahead and factor that 4 out. So I've got a 4 in the denominator, 4 times 4 plus x to the fourth. And then that 4 in the numerator. And so those nicely cancel. And that means I'm only working with x over 4 plus x to the fourth. And I'm thinking u squared equals x squared, x to the fourth. So u equals x squared, and du is 2x dx, or dx is du over 2x. Notice the x in there, and that's going to become important in our next step, because we've got 4 plus u squared, and then du over 2x. So our x's cancel, and I get 1/2 integral du over 4 plus u squared. So they just asked us to say what formula to use. And one of their formulas was integral 1 over a squared plus u squared du, our basic inverse tangent formula. So that's the one we would choose notice that they are not putting this 1/2 in their formula because they don't need to. If you were actually working through and finishing up the problem, you would need to include the 1/2. But in terms of which formula to use, it's still that same formula. Does that make sense? So for the formula piece, you only have to look at the integral you end up with, and that matches that. All right, I think we are in a good place to stop here. So for this week, let's see, some of you still need to finish up your test, I know, so make sure you do that if you didn't do so already. This next section, other strategies, deals with the tables and then using either Mathematica or Wolfram Alpha or your calculator to calculate integrals. And then next time we're going to look at numerical integration, so approximation methods, and then we'll do improper integrals, and that'll clean up the rest of chapter 3. And then your test window coming up is going to be like the 26th through the 29th, I think, is what I have for the midterm exam.
Is that over all the past like 3 tests?
I'm sorry?
Is that over like the past like 2 or 3 tests that we've had?
It's over everything since the beginning of the semester. It's a,
all right,
it's
thank you.
truly a
questions.
Truly a midterm exam. I don't know. I didn't write it yet.
Okay. And is that going to be online too?
That is not going to be in Alta. That is going to be a paper pencil kind of test that you're going to write and you're going to upload into e-learning.
So okay, so we're going to print it off or whatever?
Yeah, you're probably going to print it off and then write it out and then scan it back up.
Okay, cool. Thanks.
You're welcome. No, Merrick, it is not timed. So a little bit different format. It's sort of more like a normal test format, except that you get to do it at home since we can't use the testing center or the classrooms. Other questions? All right, I am going to let you guys go then for today. I will see you on Wednesday if I don't see you between now and then. And finish your test if you didn't do so already.
Okay.
All right.
Okay,
Can I talk to you, Phoebe?
You sure can. I gotta pick up my pencil.
All right.
I lost it. Aaron C, let me see. The homework we just covered is due next Monday. Do I have a suggested due date? I can't remember. Let me see. Back a page. Oh, that's really gonna take me. There we go. Here we go. Yes, next Monday was my suggested due date. Remember, none of those due dates for the homework are set in stone.